Welcome, everyone. Today, we are diving into the future of self-evolving AI. I'm excited to introduce you to T-3RL, which stands for Tool Verification for Test Time Reinforcement Learning. Let's explore how we are bringing verified intelligence into the next generation of reasoning models. Let's start with the big picture, scaling beyond labeled data. We are currently witnessing a massive paradigm shift. Large reasoning models are evolving through test-time reinforcement learning, or TTRL. This means we are moving away from relying on vast, human-annotated datasets, and instead, moving towards systems that adapt on the fly. The mechanism is simple. The model generates multiple reasoning traces for a new problem, votes on the best one, and creates a pseudo-label to learn from its own generated data. The ultimate goal is to create autonomous systems that continuously improve without human supervision. But there is a catch, a major vulnerability we call the fatal flaw of unverified consensus. When a model's internal reasoning is biased, simply agreeing with itself doesn't mean it's right. We call this false popular mode collapse. Imagine the model samples 10 predictions. The true answer is C, but the model's flawed logic repeatedly outputs B. By relying on a simple majority vote, it rewards the incorrect answer simply because it's the most common. This creates a dangerous cycle of reinforced bias. Once that incorrect pseudo-label is set, the reinforcement learning update makes the model even more likely to sample that wrong answer in the future. The model grows increasingly confident in its own incorrect estimations. The result is a vicious cycle that drives the model into an incorrect mode collapse, making internal self-correction almost impossible. So, how do we break this echo chamber? Think about how humans solve this. When our own intuition isn't reliable, we seek external evidence. AI requires the exact same capability, which is test-time verification. By interacting with an external environment, like a code sandbox, the model breaks out of the closed loop of self-consensus and anchors itself in grounded, verifiable evidence. This is where T-3RL comes in, enabling evidence-grounded self-evolution. T-3RL integrates tool verification directly into the aggregation mechanism of test-time RL. Instead of blindly trusting the most frequent answer, it validates the model's reasoning traces by offloading the computation to deterministic external logic. As a result, the learning shifts away from frequent but flawed answers toward verified, truthful modes. T-3RL is built on three core pillars. First is the verifier, an LLM that extracts the candidate answer and transforms the reasoning trace into executable Python code. Second is the verification tool, a deterministic code interpreter sandbox that runs the Python program to provide external evidence. And third is the verification weight, or omega. This replaces simple majority voting with a verification-aware weighted vote, boosting the power of verified rollouts. Let's look at the architecture in action. First, we sample multiple paths from the policy model. Next, the verifier translates these answers into Python queries. The sandbox then executes the code, returning deterministic evidence. Then comes the weighted vote. Verified answers get a boosted weight of omega, while unverified ones get a standard weight of 1. Finally, the RL update calculates the reward against this robust, verified pseudo-label. The results are highly impressive. We see unequivocal gains across benchmarks. T-3RL consistently outperforms baseline TTRL across all evaluated backbones. We achieved an overall average relative accuracy gain of 11%. Most notably, on the hardest benchmark, AIME 2024, we saw a massive 31.6% relative gain. What's fascinating is that harder problems actually yield bigger interventions. The relative improvement of T-3RL scales directly with the dataset's difficulty. Harder math problems require longer computation chains, meaning the reasoning is much more vulnerable to accumulating errors. tool execution steps in to provide deterministic checks precisely where those intermediate steps are most likely to derail. Now, you might ask, does the model just need more time to think, or does it actually need the tool? Why isn't double-checking enough? We isolated this effect by running the verifier LLM without the code execution sandbox. The result clearly showed that while self-verification provides a minor lift, it's the true executable evidence from the code sandbox that drives the vast majority of the performance gain. Let's talk about how much we should trust a verified rollout, what we call the Goldilocks verification weight. If our weight, omega, equals 1, we degenerate back to standard majority voting. If it's infinity, we over-index on verification and become brittle to tool imperfections. The optimal balance is an omega of 5. This moderate confidence boost prevents false popular answers from dominating while maintaining the diversity we need for learning. T superscript 3RL also delivers maximum signal with minimum compute. In terms of compute efficiency, T superscript 3RL surpasses standard TTRL doing 64 rollouts by using only 16 to 32 rollouts, simply because verification dramatically improves per rollout quality. Furthermore, it vastly improves training stability. Anchoring rewards with tool verification drastically lowers variance, yielding highly consistent learning dynamics. There is, however, a cost if you use weak verifiers. T superscript 3RL requires a minimum verifier capacity of greater than 0.5 billion parameters. Deploying undersized verifiers can actively degrade performance. Small models suffer from blind copying, where they hallucinate reasoning and just print the unverified answer. They also suffer from syntax errors, failing to write valid Python code, resulting in compilation failures. To conclude, T superscript 3RL is much more than just a training loop. It is a mechanism for generating verified synthetic data on the fly. By decoupling reasoning from tool execution, we transform standard sampled rollouts into highly reliable, evidence-grounded training instances. Ultimately, test-time tool verification is the key to stabilizing the next generation of self-evolving reasoning models. Thank you for watching.